Greetings and welcome back. I'll begin by giving an overview of the 4 topics that make up the first section. Begin by looking at the physics of projectile motion. Then we will move on to uniform circular motion. This involves the physics of centripetal acceleration and centripetal forces. And we use this to explain the physics of banked curves. Satellites are an example of uniform circular motion, and to help explain this motion, we will use Newton's law of universal gravitation and the application of centripetal forces. The final topic focuses on momentum, and we begin by looking at the change in momentum and how it is applied to Newton's second law. We finish by looking at the conservation of momentum law and how this can be used to help explain the motion that occurs in collisions and explosions. To begin the topic of projectile motion, we must first have an understanding of vertical and horizontal components of velocity. To help with this, I have a number of clips from Hewitt and Owens that I have made available to you. The key points are that the horizontal component of the velocity remains constant. In other words, there is no external forces acting upon it. The vertical velocity, however, is going to be affected by gravity. To illustrate this, we are going to do a question from the 2013 exam. The question asks us to show that the projectile did not undergo any horizontal acceleration. To do this, I'm going to draw a series of horizontal components which represents the horizontal distance travelled by the projectile between each flash. Since the horizontal components are constant in length and the time between flashes is also constant, this means that the horizontal velocity remains constant, which means that there is no horizontal acceleration acting on the projectile. 3 things we want to be able to calculate about projectiles is the maximum height that the projectile reaches, the time of flight of the projectile, and the distance that it is covered horizontally, which we refer to as the range. To help with the calculation of these 3 values, we must first resolve the velocity vector into its components. We do this by doing trigonometric calculations, and both Hewitt and Owens have clips to show us how to do this. The vertical component is the most important of the 2 components, as we can use it to calculate the maximum height and the time that it takes for the projectile to reach that maximum height. To calculate the total time of flight, all we will need to do is double this value. This question comes from the 2010 physics exam. The projectile is launched from ground height with an initial velocity of 16 meters per second, as I've indicated here, and on the diagram. It is launched at an angle of 40 degrees above the horizontal, which I've also shown on the diagram. In part A, we are asked to show that the magnitude of the horizontal component of the initial velocity is 12.3 meters per second, and also that the magnitude of the vertical component of the initial velocity is 10.3 meters per second. We will need to use trigonometry in this question, so I've added a diagram to help. Now, the horizontal component is the first one I'll look at, and to determine that, the formula is V times by cos of 40 degrees, and the vertical component is going to be equal to V times by sine of 40 degrees. To verify the answers, all we need to do is substitute the values into the equations. For the horizontal component, this will be 16 times the cos of 40 degrees, and make sure you have your calculator on degrees, not radians. You'll get an answer of 12.258, and we can take this to significant figures of 12.3 meters per second. For the vertical component, from our graph we can see this is going to be Vy is equal to V times sine 40, which will be 16 times sine of 40. And as an answer, when we have finished, we will be able to verify that it is 10.3 meters per second. Now, the range is calculated using the horizontal component of the velocity. Since it is independent of acceleration, all we will need to do is multiply the value for the velocity by the total time of flight, and this will give us the range of our projectile. For this part of the question, we're asked to determine the range of the projectile. To do so, I'm going to use the horizontal component and the time of flight, which is 2.10 seconds. So the range is going to be equal to the horizontal component, Vx, times by the time of flight. Now substituting in our value for Vx, so I'm writing in the complete value 16.0 times cos 40 degrees times by 2.10, and this gives me an answer of 25.739, which we can write as 25.7 meters. To complete our understanding of projectile motion, we have to look at the effect of air resistance. We don't need to do any calculations with air resistance, but just to describe the effect that they have on the path of our projectile. Now, air resistance is going to reduce both the vertical and horizontal components of our velocity. By reducing the vertical component, this means that our projectile is not going to reach the same height. This also means that it will take a shorter period of time to reach there and will reduce the total time of flight. The effect of reducing the total time of flight and having a smaller horizontal component will mean that our projectile will not travel the same distance horizontally, so it will have a smaller range.